Today I am going to present to you efficient tracing of cold code via BiasFree Sampling. This is joint work done together with my advisor George Candea at EPFL and Tom Ball, John Erickson, and Musuvathi at Microsoft Research. So why do we want to sample cold code? Well, because cold code is by definition not well tested, and therefore bugs typically tend to lurk in it. Also, we don't know a priori which portions of the code are cold versus which portions are hot, and by definition, cold code is rarely executed during program execution. Therefore, we need to be able to efficiently sample cold code, as this information can help developers focus their testing and reviewing efforts towards such code. Since cold code can only be determined at runtime, we need to dynamically sample it. And there are various approaches for doing so. One approach is to statically instrument the code and dynamically sample all instructions, much like what Gcov or BBCover, which is a Microsoft tool that is similar to Gcov, do. However, as static instrumentation is always there, it typically incurs a lot of overhead. And another shortcoming is that it requires separate binary builds, and it introduces maintenance problems. The second approach is to perform the instrumentation dynamically, such as using a tool based on the pin instrumentation framework. These tools also tend to have a lot of overhead because once the instrumentation is there, they do not remove the instrumentation. And also handling multi-threaded code, which such systems ends up becoming tricky because they tend to stall all threads while inserting the instrumentation to preserve correct program semantics. Another approach is to perform temporal sampling, which can be implemented using either static or dynamic instrumentation or a mixture of these techniques. This approach samples code at runtime for the desired time interval to reduce the overhead. Although this reduces the per execution overhead, one now needs lots of executions to catch the rarely executing cold code. The bottom line is current approaches to sampling cold code are inefficient and they do not scale well. So how can we sample cold code efficiently? This is the main question we're trying to answer with this work. And the key idea we use is to put a breakpoint at every instruction, at every basic block in the program. So breakpoints are a facility present in all modern CPUs, which makes them readily available pretty much on any platform. Also, when a breakpoint is removed, it no longer incurs any overhead. So we can place the breakpoints at the beginning of the program or at any point during the execution of the program. This way, the next time any instruction of interest is executing, meaning any instruction with a breakpoint is executed, we can sample that instruction. And what we mean by sample is that we can mark the execution as having executed if we're measuring coverage, or we can record the access memory address if the instruction is a load or a store instruction. Then once we have enough samples, we can actually remove the breakpoint, and if that same basic block executes again, there will be no overhead due to sampling. But this sounds all nice, but building such a system comes with various challenges. The first challenge is that such a system should make sure that the semantics of programs and services such as debuggers do not change. The second challenge is the sheer number of breakpoints that such a system needs to handle. Think of it, in the worst case, all the blocks in the program may end up executing during a given program execution, meaning that such a system would need to be able to handle such a high volume. The third challenge is properly handling multi-threaded code. So typical instrumentation, as I just mentioned, stalls threads while inserting instrumentation in order to provide a consistent view of the executed code. But this is overly restricted for some applications, and these large overheads can be avoided if breakpoints were to be used. Finally, the managed runtime optimizes managed code during just-in-time compilation. Therefore, managed code cannot be really handled like native code. To sample cold code efficiently while overcoming these challenges, we built the BiasFree Sampling Framework, or BiFS for short. In the rest of this talk, I'll first talk about the design of BiFS. Then I will detail its implementation along with how we overcame various challenges that I just mentioned. Finally, I'll talk about some of the evaluation results. But let me mention in a nutshell that we built our BiFS framework for both native and managed code, for both the kernel and user space, for both x86 and ARM, and we evaluated it on 679 programs. And it only incurred 1 to 6% runtime overhead. OK, so let's begin with the design of BiFS. So the high-level design goal of BiFS is to be able to sample cold instructions without oversampling the hot instructions, and sample all the other instructions independently of their execution frequency. For instance, consider the example code snippet shown on the slide. Let's assume that for this particular piece of code, statement 2 only gets executed once every million iterations of the loop. Now, what BiasFree allows us to do is to efficiently sample statement 2 without oversampling statement 1. Imagine that we want a single sample from both statement 1 and statement 2 in this example. And despite the loop executing 1,000,000 times, BiasFree would allow us to obtain these samples with 2 breakpoint firings if we put a breakpoint at both statement 1 and statement 2 and remove it after the execution of each statement. So BiasFree sampling has 3 key parameters that allow it to achieve this high-level goal. The first parameter, k, ensures that the first k executions of any instruction are always sampled. You can think of k as the number of logical breakpoints on an instruction. Intuitively, since k bounds the number of samples generated per instruction, it also bounds the overhead of BiasFree. Essentially, BiasFree won't incur any overhead after the first k breakpoint firings. The second parameter, p, is the sampling distribution. Among the instructions with non-zero probability of sampling, p can either dictate a uniform sampling of instructions, or it can bias the sampling towards instructions of interest depending on the particular application. The final parameter, r, is the sampling rate, which controls the number of samples generated per second. Since this will allow this will control the number of samples generated, it will also control the overhead of BiasFree. Now, we have a full-fledged algorithm in the paper that describes how these parameters interact, but I will give you intuitive examples using specific parameter values here. For instance, if we have the desired sample count as 1, and if we instrument the first instruction in every basic block in a program, and we have a sampling rate of 0, meaning we don't want to sustain any particular sampling rate, because, well, we're only interested in a single execution of a basic block, then we effectively have a code coverage measurement tool. At another extreme, we can set the desired sample count at infinity, and this way we will have the full execution tracing since all the instructions will be sampled. If we want to build a memory error detector or a memory leak detector, we probably are only interested in sampling memory instructions, and hence P should reflect that. We can adjust the rate and sample count based on the balance we want to strike between accuracy and the overhead that the system incurs. If you want full accuracy, we would go for setting k to infinity. Otherwise, we can lower k and adjust r in order to tune our overhead. Finally, another application can be a data race detector in which a sensible distribution would instrument all memory accesses that cannot be statically proved as data race free. So now we've seen in a nutshell the parameters behind BiasFree's design. Let's delve into its implementation details, which really made it possible for BiasFree to work across multiple platforms with low overhead. But before delving into the implementation details, I'll briefly give a breakpoint primer. So modern hardware contains special breakpoint instructions that tell the processor to trap into the operating system. For instance, on x86, this is the int3 instruction. And the nice thing about breakpoint instructions is that they're not larger than any other instruction in the ISA. On x86, they're 1 byte. And on ARM, which supports 2-byte breakpoints, all instructions are always 2-byte aligned. This way, when overriding any given instruction in the program with a breakpoint, you simply need to override a single instruction. The breakpoint instruction is therefore designed in such a way that its addition and removal can be performed atomically. This means that the program will either see the breakpoint instruction as being there or as not being there, and not something in between, as it would have happened if we were to use, say, the jump instruction on x86, which is 5 bytes. Now, this is of critical importance when it comes to overhead, as the placement and removal of breakpoints does not require any synchronization, whereas dynamic instrumentation based on jumps would have required that. So since BiasFree uses breakpoints to sample code, it inherently has an interplay with the debugger. And the default behavior of a program that hits a breakpoint is to either send the interrupt to the process or to the debugger if one is attached. To allow transparent operation, BiasFree kernel driver registers itself as a debugger to have first chance at processing breakpoint firings. Bypassing the debugger is crucial for efficiency, as debuggers do not tend to handle well frequent firing of breakpoints. If the actual debugger places a breakpoint, BiasFree will forward the interrupt generated by hitting such a breakpoint to the actual debugger itself, effectively becoming invisible to the debugger and allowing transparent breakpoint processing. So default breakpoint handling removes the breakpoint before resuming the sampled instruction. But this goes against one of the goals, one of the important goals of the BiasFree framework, that is to perform multi-shot instruction sampling. So debuggers tend to use the single stepping capability of processors to reset breakpoints after a breakpoint is hit. But this is a big performance problem, as all the threads need to be stalled, and the processor essentially goes into a mode where a single instruction is executed at a time. And what we instead do with our framework is to create a thread local copy of the currently sampled instruction. And when returning from the breakpoint handler, the BiasFree framework sets the current program counter to the copy of the instruction. So this allows the current thread to resume execution without removing the breakpoint, because now it's operating on the copy. And the jump after the copy ensures that the control returns to the instruction after the sampled instruction in the original program. So this way, BiasFree is able to support multi-shot breakpoints efficiently. Finally, I'll tell a couple of words regarding implementation challenges that we faced for managed code and how we dealt with them. So first, we tried bypassing the common language runtime, that is CLR APIs, and directly instrumenting managed code using breakpoint instructions. This, however, does not work because the common language interpreter, CLI, performs some introspection into the code that it's executing, and if it sees that code is changed behind its back, it will throw an exception. Second, we needed to disable JIT optimizations for certain classes of applications, like measuring coverage, in the cases where we needed a one-to-one correspondence between the basic blocks that were executed and the source code. And the correspondence would be lost because JIT optimizations would optimize away some blocks and move them around and things like that. OK, so now we went over the implementation details of BiasFree. Let's look at its evaluation. We evaluated BiasFree with a broad set of system binaries and applications, both native and managed. We evaluated a total of 679 programs. It includes all Windows system binaries, the Z3 Theorem prover, SPECint benchmark suite, and several C# benchmarks. So the first target program I will present from our evaluation is the Z3 Theorem prover. And I will describe the results of measuring coverage using BiasFree and BBCover. This means that we have a single-shot breakpoint setting for BiasFree. And let's recall that BBCover is a tool that leaves the instrumentation in the code once the code is instrumented for the entire duration of the program lifetime. The y-axis is the runtime for coverage measurement, and the x-axis is the actual runtime of the program with no coverage measurement. So we can see that BBCover's absolute runtime increases linearly with the program execution as expected, because the instrumentation keeps incurring overhead. On the other hand, BFS's overhead line is almost superposed with the 45-degree line representing no overhead. BiasFree does not incur any overhead after the first hit of a breakpoint, and its overhead is always less than 1%, with much less perturbation than that of BBCover. In summary, the main takeaway is that BiasFree's overhead is independent of program behavior. And by the way, if you think of it, it's a function of program size, because we have single-shot breakpoints in every basic block, and therefore the overhead is proportional to the number of blocks, and therefore to the size of the program. Second, we ran the BiasFree framework and BBCover on all Windows 8 system binaries and measured coverage. This is 665 binaries for x86 and ARM, including 32-bit ones as well as 64-bit ones. These binaries vary greatly in size in that they're binaries with 70 basic blocks up to binaries with 1 million basic blocks. Our test ran for a total of 4 hours on 17 machines, and as a result, BBCover tests failed for 45 binaries because the excessive overheads it incurred when measuring coverage caused those tests to time out. For all but 40 tests, BiasFree reports more coverage, and in the cases where coverage was less, we determined that this is due to test non-determinism. Perhaps more importantly, the coverage measurement overhead of BiasFree framework was always below 6%, which makes it a practical tool. Finally, I'll show the use case where we extended BiasFree to create a logging and tracing facility for basic blocks. To do this, we store the order in which breakpoints fire in a log by logging the basic block identifiers to a file. The y-axis in the scatter plot shows the function ID, which is a unique ID per each function in the program that gets executed. And the x-axis shows the basic block index in the log. So the patterns of lower triangles represent the blocks of a set of functions that execute close together temporally. And they naturally identify the phases in a program's execution. For the particular example of Z3, BiasFree identified the 6 phases shown on the graph. So this simple analysis shows that a one-shot logging can be used to identify sets of related functions, since it gives an interprocedural view of the control flow behavior of a program. We intend to use this information to identify performance bottlenecks in a program, as well as improving job scheduling in a data center. In conclusion, we presented BiasFree sampling, a low-overhead technique to sample cold code that leverages the breakpoint support. Since it's leveraging the breakpoint support, it's ideal for multi-threaded code, and breakpoints allow us to have dynamic instrumentation. Hence, we do not require maintaining a separate build for using this instrumentation framework. We've implemented BiasFree on multiple platforms for both 32 bits and for 64 bits, for x86 and ARM, for kernel and user space, and supporting native and managed code. We also did a comprehensive evaluation on almost 700 programs, measuring coverage and tracing the execution order of blocks to show that our BiasFree framework incurs a very low overhead between 1% and 6%. This brings me to the end of my talk, and with that, I'd be happy to take your questions.
Ashwin Goel, University of Toronto. Really interesting work. I was curious for your multi-shot support, whether you required synchronization for multi-threaded code.
Yeah, so the application, the particular application itself may require synchronization indeed. Like even with single shot, you may require synchronization if your sampling requires you to do things atomically. But the synchronization that you don't require is when you're inserting and removing the breakpoints.
Right. So for the single shot, I can understand that. But for the multi-shot, presumably you're decrementing some counter.
Yes.
So that requires
that requires synchronization. Yes.
All right.